And last but not least for this session, Christian is going to talk to us about history repeating itself.
Okay. Hello, so my name is Christian, and I'm going to talk about some ongoing work we have on distributed algorithm verification and how cyclic message histories are a useful abstraction for moving towards more automated verification in this area. And so to start out with, I want to start off with the problem statement of what are we actually looking at in this space. And so for the purpose of this talk, we're focused on safety properties, where we're interested in taking distributed systems and showing that an unsafe state is either unreachable or may be reachable. And like in most contexts, figuring out how we get to an unsafe state depends not just on the unsafe state itself, but some sort of execution history from some presumably safe initial state. But what makes distributed systems a bit more complex in this space is that rather than dealing with just one program state, we're interested in a bunch of processes shown here as circles, and the interaction of these processes can lead to something unsafe. And so on top of this, we also need to consider how these algorithms are designed in the first place. We're not interested in designing an algorithm that works with 7 processes and then redesigning it when we need 10 and then redesigning it further and further. These are all designed to be configurable. And so for the rest of this talk, I'm going to use this one-shot leader election example where essentially every process is going to start out, set a vote counter to 0, set a leader field to -1, pick a process it's going to vote for, send that info to every process, and then whenever a process gets a vote for itself, it's going to increment that vote field. When it gets more than half the votes, declaring itself leader, and whenever you receive a leader field, whenever you receive a leader message, set the field accordingly, and if you've set it more than once to a different value, throw an error. And so, importantly, this algorithm doesn't depend on any specific system size. We want this to be general for whatever sort of deployment we're interested in. And so, with that in mind, what does an execution history actually look like in these systems? We're going to look at this sort of message passing or event-driven model where each process is going to send and receive messages, and whenever they receive these messages, they're going to react by executing some block of code. And in this case, our execution history is not just the state of the program itself, but a history of which messages have actually been received in which order, which allows us to start from some initial state and essentially read off this history to reach the current state. And so the history for a particular process might be that you receive an initial message, you receive 2 votes messages, and then you receive a leader declaration. And these histories depend on the configuration. If we have a system of only 3 processes, you might see 2 votes before you see a leader declaration. When you have 5 processes, you might see 3 votes and then the leader declaration. And in general, as you get more and more processes, this history is going to grow. But it's not just growing at random. Our history is changing predictably. In particular, no matter what our configuration is, we're going to start, a process is going to get some initial message. It will receive at least 1 vote and potentially some unknown number of additional votes before it can actually receive a leader message at all. And so with that observation in mind, in this work, we define a mechanism for over-approximating these sort of cycles in distributed algorithms. And in particular, we're going to talk about how you can use goal-directed analyses with abstract message histories in order to efficiently explore the state space of these programs. We're going to show how handling cycles boils down to parameterizing these abstract histories on the configuration, and how, analogously to parameterizing the history, we can parameterize the processes themselves and end up with these sort of summary processes. And so at a high level to start out, our analysis is going to start off in some unsafe goal state. It's going to step backwards, and as it does so, it's going to build up some sort of message history and potentially add new processes that are relevant to our goal state. If it finds a cycle, it's going to attempt to summarize the messages and processes involved in the cycle. And it's going to continue this process until ideally we either find a contradiction or we find an initial state and know that there might be some error. And so the first piece of all of this is a goal-directed analysis. So we're going to start in an unsafe state and attempt to refute reachability, where in our case, the unsafe state is that you get leader messages for two different leaders. And so we're going to start off in some unsafe state and attempt to step backwards into what was presumably safe at some point. And so our goal state is the unsafe state. And we're going to leverage separation logic here, where our goal state doesn't contain every process in the system, only the ones that might be involved in the error. And so at our beginning, it might be one process that has received a leader message and has just received another leader message. We're going to build up backwards from this point and add processes as needed as they become relevant to the goal. And we're also going to build up a message history. And I'd like to point out here that this message history looks a bit different than our previous ones. In particular, when moving from a concrete message history to an abstract history, because we're only looking at some slice of the system, rather than this encoding the entire history, in between each message, you can have essentially an unlimited number of other messages as long as they don't affect this sort of like relevant slice of the system. And so we're going to start off with our one process and an empty history of, well, we don't know what the past looks like currently. And with our algorithm, the first thing we need is that, okay, well, a leader message had to happen at all. And so we're going to move to a state where, okay, some process sent that leader message, and so we're going to have that process as well, and a leader message in our history. For a leader to have occurred, someone needed to vote for that process. And so we're going to extend our history accordingly. And again, there might have been another vote. The process may have received more than one vote. Recall that every time a process gets a vote for itself, it's incrementing some sort of field. And each time we step back, we're sort of decrementing from some unknown value of votes. And so we can do that again. And we could choose to do this again and again. And what's important here is that we need to witness this sort of vote an unbounded number of times, where if we had an exact configuration of processes, we'd know exactly how many times we need to see votes. But we don't have a fixed configuration, so how many times is enough to see this vote? Whenever a process gets more than half of the votes, then we're done. But what is half? Half of what? And so with that, we're going to talk about how we can parameterize these histories on configuration. So approximating cycles isn't a new idea. It's been done in sequential programming forever, where we have some loop and we want to find a loop invariant. And intuitively, we want to try and think of these cycles as being loops. And we have a loop, we want to find some sort of invariant for that loop. And in particular, what we know is that we're going to receive a vote some number of times we'll call phi. And based on our algorithm, we know phi has to be at least, or has to be greater than half of the processes. And so we have this special message here that's parameterized on our configuration and a constraint over the actual value. And with this, we step back, we witness some unknown number of votes, and then we can continue our analysis. We've seen vote as many times as we need. There's one more piece to this, which is what about all of the processes that are actually voting? And so whenever we're stepping back, as I mentioned before, we're going to add processes to our system slice. Every time we see a vote, something needs to have sent that vote. And so if I had a fixed configuration, say there were 5 processes, I could add 3 processes to my system and step back. But we need 5 processes. How do I add 5 things into my goal state? And the thing to note here is while we need to add 5 processes, each process is going to have the same constraint initially that they need to send a message. They need to vote for the same thing. And interestingly, while they start with the same constraint, they might take different paths to reach that send, and so constraints on each process going backwards might not stay the same. And so it's not enough to just say, okay, well, all of these processes are replaced by one process. But what we can say is that while different processes might take different paths, some of them might take the same path. If I have 10,000 processes, probably some of those are going to take the same path. And if we have some set of processes that take the same path, all of the constraints over them will look exactly the same. And so rather than keeping each of these as a separate object, we can summarize them into a special process here shown PK, where PK stands in for P1, P2, and P3, and potentially some unbounded number of these processes. And when concretizing, PK will become some set of processes. And so with that, we're going to start with our unsafe process. It sees a leader message, it steps back, it sees the previous leader message, it sees a vote. Instead of seeing vote again, we recognize that if we do this, we will end up in a cycle. So we summarize that voting process, and we summarize our message history, and then we continue to step back with the cycle resolved. And so all of this sounds nice in theory. What have we actually been able to do with this so far? So currently, we've built up a tool for analyzing P programs, where P is a modeling language for message passing systems. We're able to prove this one-shot election example safe without explicitly picking a set configuration like you would with a model checker. We also expect that this approach will apply to other consensus algorithms where they have this similar sort of structure of initializing, sending some number of votes, reaching a quorum, and then proceeding, where reaching the quorum is the sort of vote cycle we saw in our first example. So we expect that this will apply to this sort of class of algorithms. But there's still some limitations, and there's some future work to explore in moving in this direction, where if we have a bound number of unique paths, then each of these we have some finite number of summary processes. But what if there's an unbounded number of these? And this can be looked at with some sort of reachability analysis. How do we get the best constraint possible on phi? How can we leverage other information we might have about the system, like its topology? What if it's a ring? And how do we know that this scales with the message history? As the system gets bigger, how can we deal with reordering some messages that might not matter for our goal? So that's all.
I have not understood how you get your phi. I have a suggestion. When you have a loop, you add a counter, then you make a relational analysis. It's related variable to the counter. You eliminate the counter, you get it. You have a similar technique or no?
Yes, in the implementation, we're currently leveraging a recurrence analysis to sort of solve out for a closed form solution of what phi needs to look like. And that's also where we get the constraint over phi, where it comes from in our algorithm, every process votes once. And so this is sort of where the reachability analysis in the future work comes into play of ensuring that there's this interplay between the reachability and the recurrence analysis to get the strongest constraint we can find.
All right. Earn your coffee break with one last question. No? An earned coffee break? All right. Well, thanks again, Christian.